Elements on the periodic table have certain periodic trends. As you go to the right on the periodic table, radius of elements will tend to decrease, and the ionization energies and electronegativities of those elements will increase. But as you go down the periodic table, radius will tend to increase, and ionization energy and electronegativity will decrease. These are due to changes in the effective nuclear charge for an outer electron to the nucleus, as well as changes in the distance of outer electrons to the nuclei. So effective nuclear charge is kind of a simplification of nuclear charge, right? So nuclear charge is just the number of protons, the charge of the nucleus. Actually, I guess more complex is effective nuclear charge. That is the number of protons in the nucleus, but then subtracting the number of inner or repelling electrons. So for example, here, this outer electron is attracted to 3 protons in the nucleus, but it is repelled by 2 inner electrons. So it is attracted to 3, but repelled by 2. There's a net attraction of as if there were just 1 proton in the nucleus and no electrons in the middle. Effective nuclear charge was that number of protons minus the number of inner electrons to give the nuclear charge. So as you go to the right in the periodic table, you will see that the number of inner electrons will stay the same, but the number of outer electrons will increase. And the number of protons will increase, like we went from 3 protons to 4. With beryllium, this has 4 protons in the middle, but still only 2 electrons in the kind of in between. And so for -2, there's a net nuclear charge of 2. So we can see that the effective nuclear charge increased, going 1 to 2. So actually, each time you go to the right, there's going to be an increase in effective nuclear charge of 1, except in the D and F blocks, but definitely in the S and P blocks. But as we go down, the effective nuclear charge won't change. So the effective nuclear charge for this electron of lithium was 1, but it is also 1 for this electron of hydrogen. There's 1 proton in the middle, but there are no inner electrons between that outer electron and the nucleus. There are no electrons in between which would repel that electron. And so it's just as if there is 1 proton in the nucleus. So kind of net. The overall effective nuclear charge will stay the same as you go down, and it will increase as you go to the right. Please note, though, that the outer electron, though the effective nuclear charge will stay the same, the outer electron will get less and less attracted to the nucleus because the outer electron will get further and further from the nucleus. The attraction between 2 magnets is greater if those magnets are near each other. But also the attraction between oppositely charged particles is greater if they're close to each other. According to Coulomb's law, the attraction between opposite charges is directly related to the size of the charges, but inversely and quadratically related to the distance between the charges. Okay, so having seen nuclear charge now, we can see that as we go to the right, as that effective nuclear charge increases, outer electrons will become more and more attracted to the nucleus, and hence they'll actually end up being drawn closer and closer in. These electrons are more attracted to the nucleus than this electron is, and so net they'll hang out a little bit closer. And so the radius will be smaller as you go to the right. But radius does increase as you go down because as you go down you get more and more shells. So like hydrogen had just one shell holding electrons, but lithium had two shells, two principal energy levels holding electrons. And so those outer electrons will get further and further from the nucleus as you go down. Now, another trend we'll see is ionization energy. This is the amount of energy required to ionize an atom, i.e. the energy required to remove an outer electron from it, creating a positive charge, creating an ion. Ionization energy will increase as you go to the right, because ionization energy describes the energy you need to pull electrons off of the nucleus. So it's harder to pull this electron off from beryllium than it is this electron from lithium, because this electron has effectively twice as much attraction to the nucleus, having twice the effective charge. So you need about twice the amount of energy to remove this electron than that. So ionization energy will increase as you go to the right. You get more and more protons holding electrons to the atom, and so it requires more energy to pull those electrons off. But ionization energy will decrease as you go down, because here this electron is fairly attracted to the nucleus, but this electron is less attracted to the nucleus. We had the same effective nuclear charge, but this electron was further from the nucleus than for hydrogen. And so it was less attracted. And hence, less energy would be required to pull it off. All right, and then we have exactly the same trends for electronegativity as we do for ionization energy. Electronegativity describes the relative attraction of electrons that are in bonds to the nucleus of an element. So like later on, we might take a look at a bond like between hydrogen and fluorine, and we'd say, oh, fluorine has, overall a greater effective nuclear charge, and so the electrons in this bond are not shared equally between them, but will hang out more towards the fluorine. Ultimately, having negative electrons hang out towards the right, we get a partial negative charge around that bond on the fluorine part, and then a partial positive charge around that bond with the hydrogen part. Having negative electrons hang out to the right more, we'll get a partial negative charge on the right and a partial positive charge on the left. So, this electronegativity is really the description of the attraction of electrons towards an element. So, it should have exactly the same trends as ionization energy. That also describes, the attraction of outer electrons towards an element. Here are some electronegativity values that you may need to use, I guess, in a couple weeks when we're determining the polarity of bonds and molecules. Fluorine is the highest electronegativity element. As you go to the right, electronegativity increases because you get a greater and greater effective nuclear charge. But as you go down, electronegativity decreases as outer electrons get further and further from the nucleus. So fluorine is the highest value, and then you have decreasing values going to the left or down. But actually, you might have thought helium might be the highest, as it is closer to the top right corner of the periodic table, but we don't know the electronegativity of these noble gases because we would need to be able to have them bond to something else and then kind of test out whether electrons hang out more towards one element or another. We can't test that because these elements don't bond with anything. They're noble gases. They don't react with much of anything. And so just kind of summarizing all of that, ionization energy will kind of increase as you go to the right and also increase as you go up. And so at the top right corner of the periodic table, you have the highest ionization energy elements, and then in the bottom left, you'll have the lowest ionization energy elements. Ditto for electronegativity values. And radii will increase as you go down or decrease as you go up and decrease as you go to the right. So the smallest radii elements are at the top right and the largest radii elements are at the bottom left.